Welcome everybody. The title of my talk is Relaying and Scheduling in Wireless Interference Limited Wireless Networks, and I'm going to present some results based on my thesis. The first part of work is half-duplex relaying with downlink cellular system. This is joint work with Jerry and Ronaldo at Bell Labs, and my advisors here at Lab. So by half-duplex, I mean those relays which cannot simultaneously transmit and receive in the same band. Okay, so the question was, we started out with is that do relays really help in interference limited cellular systems? So there is a lot of work in the literature, but a bird's eye view shows that effective power gain due to reduction in distance-based attenuation, relays could help there, and also diversity benefits due to relay transmissions. But one major disadvantage in this is that it can increase the effective interference due to in-band relay transmissions. So interference limited settings bring this problem in, but noise limited settings, we can easily show that relays give us gains. So okay, so let's then we thought, okay, we should go look at the literature. What is relaying? There's quite a bit of study in the literature. One is the information theoretic bounds. It's been there for 30 years now. Core and Gamal, which in 1979 they proposed the relay channel, and further work, lot of work, latest work. This is a very good paper by Kramer, Gaspar, and Gupta. And again, if you look at the scaling laws in its asymptotic regime, Gupta and Kumar started this work, and they talk about relays too. And in the communication theoretic literature, they talk this called user cooperation diversity by Lahnemann, Shea, and Warnell, and Centralized, Erkip, and Argine also gave this user cooperation diversity. That also took up, and it was studied well in literature. And the systems people talk about multi-hop architectures on scheduling and relaying. And if you see the industry, there is a lot of work on simulation study on cellular relaying in academia and industry. The standard is ongoing now. So we present a simulation study in this work where we compare two systems. This is a sample system. We actually study a bigger system than this, where a baseline where there is users in the cell, and also we put relays in the system, and we going to study and compare the benefits of relays. So here relays help to deliver the message to the users. Okay, so we studied two schemes in broad. One is a collaborative power addition scheme, where the relays get the message in band and transmit to the users. So in that we study two subcases where we call PCPA, which is a peak power transmission with CPA, collaborative power addition, where we have full power transmissions, and because of full power, because of the various locations of users and their shadowing, they get variable rates, and we allow for 10% outage. I'll explain more about outage later. And a PCCPA scheme, which is a power control scheme where we can have a target rate, and we do power control to achieve that target rate, again allowing for 10% outage. And we also study a very simple scheme, and to see how this scheme compares with the collaborative power addition scheme, which is a little more complicated. So where the base station relay transmit in orthogonal time slots. So you can think of a multi-hop going 2 hops, and where the base station transmit with peak powers and relay perform power control to achieve after they get the message in the second time slot, they achieve do power control to achieve fixed rate. So basically in this talk I'm just going to talk about the PCCPA scheme, where we do power control, the base station power control to achieve a target rate, and after the users, the relays get the message, they going to jump in and do a joint power control with the base station to achieve the common rate. And we take a rational approach for discarding users in the system, and we'll present 2 experiments. One is the power savings to achieve a target rate by putting relays, how much power savings we get in the system, and also how much common rate we can improve by putting relays over the baseline.
This is a slotted system, right?
Yes. No, this is not a slotted system. The orthogonal relaying is a slotted system.
The orthogonal relaying is a slotted system. And in practice, how big are those slots? I'm worried about propagation differences. And I'm really asking everybody because I don't know.
Yeah. So basically, the slots can be like based on the system specifications. Maybe you can have orthogonal time slots, for example. The base station can transmit in one time slot, maybe a second or something. But I mean, you have to average over the small scale fading though, where the large scale fading like keeps this constant.
I'm just wondering how you keep everything in sync. I mean, there's usually timing advance.
Okay, yeah. So basically, I assume that there is a synchronization.
So you're just taking that as a given.
Yes. Well, I mean, in the starter system, we need synchronization. Otherwise, it's going to be a mess.
Yeah, I just don't see how does that work.
Current US cellular is all synchronized.
No, that's fine, but when you know
So
relays.
It's supposed to be an add-on to an existing cellular networks where the relays will get their timing from the base station, pilots and otherwise.
So could you, I'm sorry to hold you up here, but go back to the picture where you show the relays. So right in there, so for example, the timing advance from that triangle to the relay and that triangle to the base is different.
No. So let's take one. Maybe we should wait for Chandra to give his thought. But each relay determines what base station it ought to associate with as being the one with the least propagation loss, and it's going to derive its timing from it. Now you could conceivably have another transmission that is happening while that relay is listening. But that's likely to happen so far away that it's not going to cause significant impairment.
All right, so I'll suspend disbelief. We'll just assume that it works.
Or assume it's given.
Basically, if it's CDMA, then if it's off by a little
I'm
bit,
not worried.
yeah, then and if it's OFDMA, then it's within the CP. Okay.
But also, I think it's important to keep a sense of scale.
Yep.
The time slots are ordered millisecond. The propagation
That's
delays
really the
are
question I'm asking.
ordered microseconds.
Yeah, no, got it. That I got. And that's what you're telling me. Now I'm happy.
Yes, so basically, we can over control channel also give this timing information. So that
It's the physics that I was worried about.
Okay.
I think Ronaldo kind of nailed it, for me at least.
okay, so basically,
I'm going in for that assumption too.
okay, so basically, let me give a very broad overview of what the coding strategy is. We are assuming a channel analysis based on the codes such that the mutual information at the receiver corresponds to the sum of powers if both the base and relay are transmitting, it corresponds to the sum of powers from the base and relays. So there exists codes like that, but I'm not going to go into the details of this. So what happens? The base is there's a Gaussian codebook with power constraint pi, and where interferences can be approximated with Gaussian noise. So it's going to transmit to the and the relay is also going to listen, and as well as the destination is going to listen to it. After the relay decodes the source, it's going to come in and then transmit using a Gaussian codebook, and at the destination the average rate is going to correspond to the sum of the powers, received powers at the received location. So basically, using this, we are going to do a system. The system overview is like we are going to simulate a downlink system with 19 cells with wraparound, and each cell has a base station at the center with 3 sectors in each cell. And we are going to consider a single server, user being served at any given time, and we're going to look at only those users who are going to share the same band at the given time. And when relays are present, we are going to have omnidirectional relay antennas and one relay per sectors. We are going to assume these relays can be built very in a cost-effective, very inexpensive and all these things. So, and we are assuming low power relays. And we do not consider multi-user scheduling, MIMO gains, and all the bells and whistles are gone now. So we're just going to look at only how much gains relays are going to give us. So this is.
Are you assuming that the channels are coherently adding? Are you assuming knowledge of?
No, I'm not power addition.
Just power addition.
It's just power addition. Okay, so as I said, I'm going to simulate a 19 cell, 3 sector per cell with wraparound, and side distance is 1 mile, and a bandwidth of 5 megahertz. This is more not a very real life kind of. We are going to make a lot of idealization. So these are some of the idealizations I make, and we are going to assume large scale fading with uncorrelated shadow fading, and we are going to neglect small scale fading, and the shadowing is log normal and path loss with a decay of 3.8. And outage is 10% for the base and relay. So by outage, I mean that we can allow, if there are n users in the system, we can allow 10% of the users to not get the desired rate.
And those 90% that are served, they're all served within the same resource.
Yes, within the same resource. Okay, so this is the wraparound network, and I'm going to consider this 19 cell, and these these red and yellow are going to be mirrored inside this 19 cell system. So it's going to be a wraparound system.
I'm just looking at that. So this was a simulation study.
Yes, simulation study.
20 years ago, this was impossible.
Well, now you can do 300.
This runs faster.
Yeah. So so we give a heuristic to how to populate users in the system. So the aim is to serve a user population with an association scheme. So users are placed one by one in the system. For example, as users come, as the user comes into the system, he's going to choose a base station antenna based on the best signal strength. And if the sector is unoccupied by any other user, he's going to be allowed into the system. But if, for example, the user comes into a sector and already the sector is taken, he's going to not be admitted into the system. So, and users are populated until all 50% sectors are occupied. Okay, so the relays are placed one in each sector at best known locations. The best is like we look at all possible locations. For example, I tried many places from base to the edge, and I found some that halves the cell radius is a reasonably good location to place the relays, and it's in the direction of the main lobe of the base station sector of base station antenna in each sector.
But every relay is placed in the same location relative
Yes.
to the base station.
Yeah, I'm not doing it one
It's
by
not based on the sample that you drew for the shadow field, for example.
Yeah. So and relay brings in additional power to the system. So basically, we assume that there is power available, for example, on a rooftop or on the top of a building. And they transmit around close to a watt.
There's not something that you can just do. I guess what bugged me was you said best location, so you saw me mounting best, and you explained what best meant. But what you did was you checked.
I just checked over simulation. It's not an optimal.
The management just said that there's no issue about a particular sample of a log normal fading, so there's a symmetry, right? So you're in a sector.
Yes.
One part of the sector is different only by the geometry. Is there any analytical thing, or is it that is there an analytical result that corresponds to this, or it's just simulation? I shouldn't say just simulation, but
It's only simulation. I don't have now.
But isn't it by inspection that given the symmetry of the problem,
I'd
we
expect it to be along the main line.
right? Well, at some radius.
Right.
Right. And the only question is, should it be anywhere but the middle?
Yeah.
Yeah,
No, but if you do it on a sample by sample,
So
basis, it's very different. answer.
Yes.
No, of course.
No, I'm not questioning
but
the
if you
result.
have to
I'm just
do,
curious if there was just a
I
clean
think
analytical way to
Chandra
do it.
just sampled, a number of locations and was very smooth. And,
Yeah. This is. I mean, I'm not claiming to be the optimal.
Oh, no, I'm just
Yes.
curious.
But-
That's all.
Let me add to the discussion. There is a beautiful problem, given that new students are starting, which is what you just said. But it requires to have not just log normal, but correlated log normal.
Yeah.
And so that and the notion is very intuitive, but very difficult to actually articulate rigorously. You would want the relays to help users at the bottom of a hole. But how do you define a hole? Is a hole for this base station, for the other base station, for all the base stations? And then on top of that, if you did define a hole, a propagation hole, where do you put the relay optimally? Because if it's too close to the user, it's not going to get the signal from the base. If it's too high up in the reach, it's not going to help the user. So it's somewhere around the crest of the hole. Those are very intuitive statements. To try and put rigor and quantify that, it's non-trivial.
There has to be a hole to all the base stations.
Right.
Look, I'm sure there's some spherical chicken arguments that you could live with that would work this out.
Well, but you can have ridges. The quote-unquote propagation holes are in our brains. Maybe you look at real topography and you see valleys, you see canals.
No, I guess what I'm saying is that there's probably an analytic version of this that will lend itself to analysis that's a cartoon, so a spherical chicken, the old physicist joke. Consider a spherical chicken.
Right.
The usually is indicated by triangles. That association is made on the basis of log normal. They can be outside the geographical
There's
area.
no
That is
distance.
purely propagation distance as far as they're concerned.
Yes.
And is the association in the relay case, every user does make use of the relay? I guess it's not a disadvantage to using the relay. There is, right? Because you are interfering with the.
Yeah, but the thing is, okay, here the association is based not on relays. We assume that the user doesn't know that relay is going to help him. He's just going to associate with the base station.
In the relay results, every user is getting the relayed signal.
Well, see, the relay may
If the relay is
too late and be useless.
eligible to
If it
help
helps,
him.
if that's a bad shadow.
There is an eligibility for, I'm going to talk about it. If the relay is eligible to help him, he will help him. Or not.
Okay, you're worried about
Right,
it later.
right. If he can't help, he will help, otherwise he doesn't help.
Okay, so this is the baseline system I'm going to consider for this power control CPA system. So basically, let's assume that there is a required to provide a desired common rate to all users except for those users in outage. So basically, I discard 10% of users, such that 90% of the users get feasible power allocation to guarantee 1 bit per second converts. And the 1 bit per second converts, like you can think of 0 dB and convert it to 1 bit per second converts common rate. And the base station is now, it's just a power control system. Base station control powers to satisfy the common rate. And then a central controller just has to solve the feasibility problems of powers, and you can get the powers.
But it's linear, which is great. So
Yeah, so it's just a simple linear feasibility problem.
So how did you pick this number? Did you check the sensitivity to it?
Of
There's
1 bit per second converts. I mean, this is just a number we picked, and it's like 0 dB is for the.
I mean, if you plot the CDF of geometries, then so this 0 dB will correspond to something like 20-25%.
Yes, around that. So basically, we are having this.
Well, it actually comes from at the very first he stated that we are looking at interference limit. So if you look at CDF of SINR for interference limited systems, a whole chunk of users are around plus or minus a few dB. So
Yeah,
it's
so
just
that
feel-
that
looks like a good.
reporting is about 20,
Yeah, 20th percentile maybe. So basically, I'm looking at those users. I want all users to get that common rate. Basically, I want to get all users to get that common rate. Basically, but for the outage users. So this is this a fair system.
It's a very, very high level one-line modeling of what current systems are doing.
You sort of beat you up about the basic stuff, but this is, this is where most of the work comes, and the rest is wonderful frippery. I just want to understand the basic ideas.
Yeah.
The intersite distance was what?
1 mile.
Chandra, may I ask, sorry, an even more fundamental question than Chris asked. I don't understand whether the relay, in your assumption, transmits the same information virtually simultaneously with the base station, or whether there is a store and forward situation where a signal is received by the relay stores it and retransmits it. And the other question is the receiver doing optimal combining of their signal that it receives from simultaneously from the base station or even with a delay? As the relay, or it relies on either one or the other?
So for first question, it's neither of them. So the relay is not actually going to store and forward, and it's also not going to transfer the same message with the base station stuff. It's actually a code. You can think of a code which, for example, I can build at the base station and the relay. And as soon as the relay gets the relay, for example, it's closer to the, for example, let's say the relay has a very good channel to the base station. It can decode the 4 big code word in lesser number of symbols, and then now it knows, okay, what exactly the message is. After that, it's going to transmit another code word or something. So that it's going to transmit also, and the base station also going to transmit. And there is a decoding strategy. It's like a Gaussian decoding strategy. It's not combining, or I'm not going to.
There's no coherence, which
No
was
coherence.
established.
So basically, it's no. It's not a relay combining scheme. So but after you decode at the receiver, the mutual information, the average mutual information is going to correspond to the sum of the powers at the receive location. There exist codes like that. I'm not going to go into.
So essentially, you are assuming optimal combine, that the receiver does optimal combine.
No,
Did you
no,
define
no.
that?
This is like, think of it like a multiple antenna system, where there are 3 transmit antennas, one corresponding to the first phase when the source is transmitting along, and the other 2 corresponding to when the source and the relay are transmitting. And those 2 are at the receiver. You only have one receive end. It's like you have two receive antennas, one receiving the first phase and the other receiving the second phase, where it's getting two transmissions. So it's like as if you had three at the transmitter and two at the base. I'm juggling time to recreate a spatial system.
So the base station transmits, let's say, a code word. The relay decodes the code word after it has it exactly right.
That's right.
It retransmits the same thing.
No, it retransmits the same information, but not the same code word.
So let me help. If you so the first part is trivial. It's until the relay gets the message.
Right.
From there on, it's better to think as a 2-1 and a multi system, which the receiver is going to respond to the sum of the powers.
Okay, so
how exactly is done? Well, unit decoding that goes behind.
So when the relay transmits, the base station transmits simultaneously with the relay.
But with a different code.
With a different code. Right. The same information.
The same, right.
So it's kind of a two-step, you would think.
Absolutely.
But these are going to happen at different times. Each relay in the system is going to get information at different times. So you don't have to have a slotted system. So in this case,
the reason this is interesting because a different model might be that the base station transmits, the relay retransmits, but during the retransmission, the base station transmits other stuff to other users.
Yes.
Because
we studied something about thermodynamics thing, but in that the base station is not going to go ahead and transmit because our system I'm going to consider only the base station has to only serve one user here. I mean, if you have a system where there are multiple users to serve for the base station, the base station can go ahead and it jogs over after it reaches to the relay and relay takes care of it, and then the base station takes care of okay, I'll start the next. But this is what we are studying here.
So we've established kind of the basic practicality, but the whole point of this is to cut to the chase and use a power adding mutual information sort of metric.
Yes.
Right. Yeah, I mean the whole objective was assume that such code exists. Is it even worth pursuing this given the gains that you would not protect?
But such codes do exist.
They do
We're
exist.
not experts on
No,
it.
great.
I just want to get the capsule.
Yeah, we know they exist, but we're not going to
Right,
go
so the
down
mutual
this
information, as you said, is summing according to an elevation of the power equal to the sum of the two powers.
Sounds good to me.
Did you answer?
yes.
Okay, so basically,
You're getting the real old Bell Labs treatment here. Just telling you.
The old part is
This
really
was
bad.
like we're back, you know.
okay, and so basically, when the base and the relay power dynamically operates to reduce the peak power of the base station, it leads to peak power savings. Basically, the practical implication is the leading to reduction in the amplifier costs, the power amplifier costs. And we can also choose optimal powers to reduce the average energy expended in the system. So this leads to reduction in electricity bills, which the carrier pays.
Okay, now that just wow. All right, that's a new metric. How to ask this politely? Is this real? I mean, these are
Why not?
clearly there's, but I mean.
Okay, that is idealization in the system, but basically
It's
people.
not really what I'm asking. I guess is it like 10%, 1%, 100%? I mean, how?
He's going
I guess
to.
I'm not sure what results I got.
All right, good.
So
Sorry.
it is said that about a third of the OPEX of current service providers goes in electricity bills. So they are really, really serious
The
about
transmission.
total.
I think we have some pie charts at some point.
And in macro cells, the RF power.
So okay,
is
this
one
is
big
important.
chunk of it.
All right, no, okay.
I just because you asked me this question, this is a backup slide though. But I mean, this is a pie chart we got from a green radio project in the Europe, where the Vodafone is the service provider, and for example, 57% of the total power in cellular systems is consumed at base stations. And basically, if you break up the pie,
Thank you.
this is the
Actually, Steve Wilkes,
yes.
I think you were also in the email that we exchanged. He claimed these numbers are wrong and it's actually much worse.
Okay.
So he has some other.
So this
pie
is the
chart
power
that shows the
amplifier
numbers being
is
used.
22%. These three combined give
Right,
more
so
than 50% of what.
this is really fascinating to me.
He says half.
Yeah.
How much of that is, so how much is there? Howard, there's a lot of stuff. Should I shut up and wait?
I think so, and let me explain to you why. We are missing a whole other dimension, which is what kind of deployment are we talking about? If it's a 1 kilometer or 10 kilometer intersite, you get a very different answer than if it's 100 meters. And there's a whole debate. Are we talking about these sites that exist today or the ones that may exist 10 years from now? hey, for what I hear, 10 years from now we may be talking about 10 meters, and there it's going to be dominated by processing power consumption, not by RF. While at 2 kilometers is dominated by RF. So it's a moving target. It's fun to discuss, but perhaps unfair to China.
Okay. Did I miss this beautiful thing?
That's not in
No.
It's not there.
So back-
It's not there in the thesis.
Okay, well,
Okay, so
maybe it should be.
basically, so this is just a cartoon for what? So basically, this is the source, relay, and destination. The base station first transmits, and when the relay comes and gets a message, it can reduce the base station power, and the reduction in base transfer power is shown here. So basically, this is to get the target rate. Okay, so this is the optimization we do. For example, to reduce electricity bills, we can minimize the sum of transfer powers. At each point in time, we can solve a myopic linear program. It's just a very simple linear program to get the desired target rate and with power constraints. So we get an average power savings of 3 dB in the system. And this is what happens. So basically, as and when relay jumps into the system, the total power in the system keeps reducing. And so this is for the minimizing the amplifier costs. We try to minimize the maximum power in the system. So this is again a linear program. And if you want to maximize common rate, we can solve a non-convex myopic optimization. Basically, trying to maximize rate subject to this. For example, you can you can take a desired rate and then keep increasing until non-infeasibility occurs. So basically, find an increasing sequence of rates, and this converges because we have bounded increasing sequence. Okay, so this is the final results of summary of all the relay work we did, and so this is what I actually discussed right now. We get 2.6 dB in peak power savings. We talked to some radio guys. We got mixed responses. 2.6 is good or bad, but I mean 3 dB is the average power savings, and 34% in improvement in increase in common rate with fixed power at the base station. So we can fix the power and increase the rate, and we can fix the rate, increase the power, reduce the power. And for the other schemes, we have results here. And one interesting thing is that the orthogonal relaying scheme is just a simple scheme, a slotted scheme where base station transmits and shuts up, relay get transmits. So that gives us good. It comes very close to what these kind of schemes where collaborative relaying and all these things. So that's something which we found here, and Jerry did some work in putting in a line network also, and he also saw similar results that orthogonal relaying performs as good as
that was the motivation
yeah.
to come to this.
To come to this.
We had seen it on a line, and we wondered if it was true here, and I was wondering if it was true here, and it turns out to be true.
But still coded or not? I must be missing something. So
There's no coded here. I mean, that's just.
It's just literally just. So you still receive two things. What do you receive?
I don't receive this. Basically, what I do is like in the first time slot, the base station transmits and the relay is not transmitting. The
I'm listening. Go ahead.
Yeah, so user is just listening and he gets some rate, and after that the base station shuts up, the relay gives the residual rate. That's it.
The relay gives me what?
Whatever is remaining. I need some. I want a target rate. As a user, I want a target rate. I get some from the base station, and the second time slot the relay gives me the rest. That's it.
So it's like a channel where your mutual information gets elevated in the second stage, usually because of the closeness of the relay. So it's like AWGN, but with two different time variance and R.
How do I know what I don't?
Yeah, I had the same question. There's no feedback on this.
There's no feedback. But time is started. But time is started. You know exactly where the relay is going to start.
But I mean, maybe I misunderstood from what you've written here. I thought that there was some intelligence in whether the base station continues to transmit or not.
The orthogonal
relaying does.
Orthogonal it definitely
does. But here it is. Here it is because it's collaborative and all these things. The base station can't.
No, what I understood.
So
optimization of two transits.
If I can add, one way to read this table.
Not that in a physical.
It's rate 1, rate 2. That's that. And you plan on rate.
That's
what you need to know is whether those rates.
The rate you get is the weighted average.
That's it.
And the way to perhaps one way to read this table is look at the bottom line, and you see there orthogonal give you 35, but power addition is 25. So so what is the value of collaboration? That was the purpose. It was one of the key questions. And this table was supposed to answer, and all of a sudden I'm not seeing the answer. But we did orthogonal and we did power addition with collaboration, thinking that orthogonal is extremely simple to implement. Vanilla, very classical. And what is the value that you get by going completely sophisticated and adding collaboration to it?
So
I'd like to read 10% text.
No, not much. Actually, it's not much at all. Basically, you get the same.
34 to 35.
So the point is, a stupid person like me, I look at this, I say, let's do the orthogonal.
That's right.
So the near far problem dominates, and the
Gotcha.
collaboration from the base that is far from the ultimate destination is worth 1% extra.
Yes.
So it may write a lot of interesting collaboration papers, but doesn't seem to be worth going after, at least in
No,
this.
good. I love it. I like that.
So I think a couple of points that I wanted to bring up. So first is, I don't have a feel for how sensitive this 2.6 or 3 dB is to the setup that you have. Did you run any experiments to see like different intersite distances, different models, different propagation exponent? Also, for example, something like receive diversity could make a difference in what that number is. So did you run any experiment? Do you have any feel for how robust this gain is going to be to different deployment settings and assumptions on things like receive diversity?
Okay, I guess let me tell you what I feel. Basically, at least if you have large intersect distances, if you are going to see a lot of interference reduction and you are more noise limited, I think this is going to go urged off because you are going to save a lot of input power. I guess the gains are going to go more higher, but all this comes because I don't know. I thought there'll be more gains here, but the gains I think are reduced because of the interference.
I mean, the questions you asked, all the kinds of questions that we're looking into in following studies, it took a lot to get these simulations, and we didn't have a chance to look into those.
Yeah, but I'm not hearing, Chandra, what it's important to realize that the standard industry practice is whatever cell site you would use enough power to be interference limited. So at least at that very high order, there's a bunch of parameters that are scale independent, like transmit power, receive SNR, receive noise figure. You would just use enough power, no matter what the deployment scenario, so that you overpower the thermal noise of the receivers and your interference limited. So the only one that remain that could indeed produce different results are the power loss exponents, for instance.
Yeah.
That would give you very different behavior.
Also, receive diversity is matter.
Yeah, the number of antennas, right? How do you play the game with additional antennas at the terminal or at the base?
I think I'm okay with this conclusion is interesting that the orthogonal domain is basically, a scheme much more practical. That's giving you similar gains. So I'm not too concerned about the relative conclusion that you're drawing, but the magnitude of the gain that you're getting is what I'm not sure how sensitive it is to some of the dimensions. But I think, as you said, a lot of people are looking at it.
Right.
A lot of the methodology goes through more into.
Also, did you consider board relays?
No, I just mentioned one simulator.
And again, we have people within the country that are considering.
Okay, so I'm going to talk about the second part, which is basically scheduling in multi-hop networks. So basically, this is joint work with Roy and Narayan. Basically, if you see interference in wireless network systems, there are a lot of different kind of networks, wireless LANs, home networks, and also this latest trend, which is sensors and cognitive radios. The physical layer is actually varied in this case, multi-access, interference channels, and orthogonal, non-orthogonal transmission schemes. So one thing is to how do we get these heterogeneous networks to coexist? And our proposal is a spectrum server which just facilitates coexistence of heterogeneous set of radios by advising them on several possible issues. So basically, these links just subscribe to the spectrum server, and this spectrum server advises them on spectrum etiquette, interference information, location specific services, optimal schedule, and many more things. So there has been at least more than 2-3 PhD thesis based on a spectrum server idea. So okay, in MinLab. In MinLab. So basically, our system model is a simple system model where users share a common frequency band, and orthogonal signal dimensions are time slots in our case, and time scheduling is used for channelization. And there is a wireless network of, let's say, L directed links. We abstract out only as directed links, and links follow just on-off schedule. So basically, they are either on or off, and they use a constant transmission power and on state. And links employ interference adaptive modulation coding, so they can do different modulation. Assume that they can do many advanced functionalities.
And when you guys refresh my memory, I remember that was a very big first steps forward, just assuming that you use this on-off model. That made our lives a lot simpler.
Yes.
Do you remember what the outer bounds were? Or if you do whatever the optimal is, I mean, is it
I'm going to talk
much
about
worse?
that. That's the whole point.
Well, if you're only considering on-off, are you also considering cases, the general cases where you could do anything? So I guess that I'm asking something that maybe predates you. So that's why I was kind of directing it to Roy and Orion. Do you remember? I don't remember what the outer bounds were.
I don't believe in them.
Okay, no, fine. That's a good answer. That's what I seem to remember, but I was just curious.
I'm a little lost. So are you saying that instead of scheduling somebody to transmit or not transmit, you would try to simultaneously schedule them at different powers? Going back to power control,
Going back to an information theory.
multi-user.
Yeah, multi-user information theory.
Okay,
So
gotcha.
yeah, thank you. That was crazy. I had a student that almost killed doing that. Escape.
So, and the interference depends on the transmission mode. We are calling it a transmission mode. A mode is just a subset of links that are on simultaneously. So here's an example. Let's consider a four-link network, numbered 1, 2, 3, 4, and possible transmission modes are 0 when it's on, and 0 when it's off, and 1 when it's on. And here's an example mode where 1, 0, 1, 0, where 1 and 3 are on. And here is the transmission mode matrix, and this is where it lies. And based on this, we can now, from the transmission mode, we can go for a data rate matrix. For example, consider the example where a Gaussian interference single-user decoding physical layer strategy, where each receiver measures its own SINR in every mode, and this is the SINR given by that. This is the binary symbol transmission mode matrix from the matrix. So, and from here we can find an achievable rate matrix for the whole system. And we get a L by 2 to the L matrix where of rates in the system. So here is an example where we construct the whole rate matrix, and let's say it's a huge matrix though, but the spectrum server knows this matrix. It's a big assumption, but so, and it includes achievable rates of all physical layer rates, and then the spectrum server has to give the scheduling fraction of time when the system.
Maybe you should say what one of those columns.
Okay, the columns are just the rate at which, for example, this is the transmission mode we consider 10110. So this particular number is the rate where link 1 gets when the 3 is on, and when 3 is link 1 gets and link 3 gets when they're simultaneously on. The other two are not on.
Chandra, what assumption do you make for background noise? In other words, I'm looking at the 4 modes in which only one link is active,
Yes.
and they have 6.666 and 6.65. There is no interference in this case.
It's not different, but the links are of the same and so they're identical links, they're symmetric links. So they get the same rate. Yes, and by itself.
So you're assuming a certain level of background noise.
Yes, it's the same background.
It is exercising log 1 plus SNR. That's all it's doing.
Yeah.
And just the other, again, we're just holding up with stupid questions. So clearly this is for small systems. Do we have any idea typically, because nobody does this yet, but do we have any idea typically how big these things could get, how many active participants you can have? Because if it's 20, now that matrix is like ridiculous.
That's one. I mean, I couldn't do anything more than 6.
Yeah, it's just a million. You know what? We're so which is not, like I said, a million ain't a million anymore.
That's right.
So the question is, when you say, oh, what are the limits? How many? Is it a computational question about how big a problem can
I'm
you
asking
solve,
both.
or-
I have an idea how big a problem I could solve. I guess what I'm asking is typically how many, what's the row rank of this, in other words, not array. How many rows are there in this matrix?
Number of links. So the number of links times 2 to the n.
No, that I got. I'm asking how big L, I guess I'm asking how big L can be.
Typical value.
Yeah, typical, and again, typical
10?
doesn't really, where'd that come from?
Indoor. I mean, I think if we are sitting in a room like this, there are not more than 10 simultaneous communication links. That's what I would.
Okay, everybody don't lie. How many people are IMing right now? Okay. So 10, 20, 20 now. 20. It could be 20. All right.
I mean, in terms of complex, 10 is actually too many.
It's two, that's 1,000 times.
I mean, if you really try to, because he has to do sort of these optimal searches over all these.
And they're not sparse.
No, once he has 10 or 20, right? 10 is a linear program with 1,000 variables.
Yes.
That's not specific.
No, I wasn't thinking of the linear program case. I was thinking of the general formulations we have.
Okay, sorry, I just
Yeah.
was curious.
The model is actually more general. So basically, we can get all the physical layer complexities or variations in this, get into this model. For example, half-duplexing, where as a node cannot simultaneously transmit to Z. Consider this particular case where A is transmitting to B and B is B is the transmitter to D, and B cannot simultaneously transmit to Z. So basically, this is the mode C matrix we get, the mode matrix. When there is both are transmitting, we get a very small rate at link 1, and C0 which is less than 1 at rate at link 1. But they are getting one unit rate when they are transmitting in isolation. So basically, this is the rate points in the rate region. So this particular thing is the C matrix for that. So this captures half duplexing and multiple access. For example, where A and B transmitting to D. When there's
So you captured half duplexing just by making sure that the middle guy is screaming in his own ear.
yes.
Okay, so G12 is huge, or
Yeah.
the power that goes along G12 is huge. To infinity, anyway. That's huge enough.
Yeah.
So why? I'm sorry. Why is it approximately 0? Why is it just 0? I mean, you didn't say G12 is large. You said it's infinity.
Yeah, I mean it's actually it should go to 0. Okay, so where multiple access now G is doing joint decoding. So basically now we can find based on this multiple access rate region, we can find the values here and we can populate the C matrix.
That's an outer bound, right?
That's only for multiple access.
But still, it's an outer bound. So where do we fit here? We fit.
So these are the points in this C matrix, and based on this we can only for the multiple access we know the outer bound.
You're right.
We know the.
And is that the actual outer bound?
Yes, this is.
That's the information theoretical outer
Yeah,
bound?
this is the rate region of max channel.
But it's because it's a Mac channel.
It's a
But
max channel.
we got an example. I mean, that's all. We got simple examples.
But the other ones were interference channels. Actually, there are some.
You were
outer bounds,
scheduling
but,
arbitrarily with interference, right? So we don't know the
not
answer.
clear if the outer bounds are completely relevant.
Okay, so now based on this we can just I'm just going to give an overview of what we do. So basically we have wireless network where there are physical layers, achievable rates on each transmission schemes based on signal processing in the receiver, and now we can there is also a MAC based on distributed centralized scheme to avoid control interference. And
So wait 1 second. In your model, do you allow for broadcast channel as well, or no?
yeah, we can, but I'm just giving an example of MAC.
No, but in your results, for example, when you do this multi-hop flow thing, can you transmit to different nodes at the same time? Do you count those transmission modes in there? Or
In the example I'm showing, I have not counted them, but we can. But if all I need to know is what the rate I get at each node. If I can do that, I can do a lot of this number concept.
You would have to tell him what your speed is for the broadcast and what rates are achievable. And then he would be able to say, you define various operating modes, and then give him the modes and would go on half-duplex.
So you've got graph snapshots, is what you're saying, and then you're routing information along those graph snapshots. And then
Yeah, and the graph snapshots would be really technology dependent on how you choose to implement some multi-user channel.
Okay, so now the question is, what are the performance bounds on wireless networks employing a variety of physical layer strategies? So a simple example, a system model for, let's consider M nodes and L links, K end-to-end sessions, described by an origin-destination pair, and set of R routes. Routes are given. You can take all the routes. So and a vector Fk amount of flow on the kth session in each of the R routes. So here is a simple example, origin-destination. There is two flows. 1 to 2. So basically, the flow 1 goes through link 1 and 2. Flow 2 goes through link 3. So that's it. So basically, we can now write this big optimization. It's simple. So basically, find aggregate rates, and then based on all the constraints, flow constraints, we can write.
So why is that? I'm curious. Why is the R greater than or equal to some K?
So this is the.
Why is that not an equality?
Okay, so basically the R can actually take the. Okay, so what I'm saying is here, for example, this link can take let's say 5 units of information, and this, if it's taking only 2, the whole flow can be only 2. So that's why the inequality comes. There can be a strict inequality there.
It's like you over-provision the physical layer radio channel to provide higher capacity than these ultimately going to put.
No, but R is the
link
rates, right? R is the link rates.
R is the link rates, yeah.
So R equal to Cx is basically saying that the rate on that link is the sum of the flows going through that link.
No, that is, the Cx is just the physical, C gives the physical rate, and X is the fraction of time. So you will get that much physical rate in the link.
Oh, okay. So R is the capacity.
R is the capacity. Okay. So a simple example, let's take a linear network, node 1 to 5, and some propagation model here. And we consider 2 decoding schemes at the receiver, Gaussian single user decoding and successive 2 user decoding. And how do you vary the interference? Just vary the distance between the adjacent nodes. And we have a half-duplex constraint. So here is this Gaussian single user decoding at node 3, and it can go 2 user at successive decoding at node 3. Node 1, and after node 2 gets the information, it can transmit, and node 3 can do. So there are many physical layer transmission modes possible, like as you said, broadcast. So okay, so this is the first graph I'm going to show. So basically, so here's the distance between the nodes of the network. So as you go, the distance increases, the rate is going to decrease, because that's always because of the distance path loss. And for single user decoding, we get this particular curve. And if you do successive decoding with strong link first, we get this red curve. And if weak link first, we get this square thing. So if you see this in a network setting, this successive decoding and all these things doesn't bias much. So here the best way to do is like just auto number of hops is just shout out to the user number 5, and here go hop by hop.
Chandra, what signal to noise ratio was assumed for this calculation?
That's a good question. I think it is around 20 dB.
20. Have you looked at what happens if the signal to noise ratio is closer to 0 dB?
I think 0 dB, this will be very close to here, right? For example, you can just take from 1 to 5. You increase the distance, that will reduce the signal to noise ratio.
Yeah, I think we're looking for intuition. I didn't hear the intuition either.
I mean, I'm a little bit bothered by the background noise being put in just as a random parameter. A land like this would not live in isolation. If you're in a situation where you have very low background noise, the solution is kind of simple. You have one transmit at a time. You have one transmitter receiver pair work at a time, because of course you get very good capacity. You never have them transmit together, because if you have 2 of them transmitting together, the advantage is very small. In practice, that's not true. In practice, nowadays, any kind of network, as we were saying before, you get maximum benefit when you operate in an interference-limited environment, which means that you have interference from, let's call them, cooperating users that you can coordinate in a bath, in a sea of interference coming from other users that you can't cooperate, that won't cooperate with you. I would find it much more interesting to see results, for example, where the background signal-to-noise ratio is very low, closer to 0 dB, because then you would start seeing substantial benefits from cooperating transmissions, from simultaneous, what do you call it, successive decoding schemes, and so on and so forth. This result is kind of, yeah, sure, of course, what else?
So what's the difference between operating at low SNR versus spreading those nodes out far apart where you get low SNR?
But spreading the nodes apart is probably equivalent to saying
In terms of
we live in an ocean.
I don't think
of
anybody's saying any
interference.
different. I just don't know intuitively what the difference in the curves would be, or did I miss something? Oh, I'm sorry. You're saying that as a function of the distance there.
As he spreads them out,
Here you go to low SNR.
So why isn't spreading them out equivalent to sort of low SNR?
It should be.
It probably is, but now in that graph, the area of interest, so to speak, which is where the distance is very large, is all scrunched up, and it's hard to see what really happens.
Well, wait, back up. I mean, hard to see. I mean, we're talking about rate now. So, I mean, it doesn't even matter. It's not log anymore. I mean, who the hell cares down there? So I think that's isn't that the answer to your question, then? That over there, everything's scrunched up, and you don't really care, and that's what it is. This shows you what happens.
Well, I still view the vertical scale, trying to visualize it in a log scale, because a 20% increase in the achievable rate is a 20% increase in the achievable rate at any point. So I would prefer to see the vertical scale on a log scale as opposed to a linear scale.
At least in this regime, right?
Yeah.
So,
So
I mean,
I'm just wondering.
I'm saying that it's anyway your rate is epsilon, and you're saying epsilon, 20% over epsilon is good enough for
Right.
you?
What I'm saying is the vertical scale in my mind should be a log scale, because what matters to me is not the absolute increase in rate, but the relative increase in rate.
So at 150, I mean, just doing the quick math, a quarter of the distance is 25%, right? So at 150 meters, you're saying that red is a lot for you. Red is a lot better than the.
Well, let me get that. So the signal noise ratio is 20 dB for one hop, right? At what distance?
I think it's just at maybe I decided on numbers. I think it's around 50 meters.
Around 50 meters. And what exponent did you assume?
2.8.
2.8. So when we go from 50 to 200, which is a factor of 4 in distance, I take 6 times 2.8.
That's 3. Let's call it 3.
Okay, so it's 80 dB. So 200 meters is close to 0 dB signal noise ratio for a single hop, right? Okay. So the interesting result is that even when you have a low SNR environment, the benefit of doing successive decoding seems to be very.
That's kind of what I was thinking.
Yeah.
Because it's not a log scale. It's scrunched up already.
Very much not there.
So,
So
the
take away all
modes
those
that are
prizes for cooperative decoding that people have done.
what you've drawn as the modes are the modes only for single user decoding.
The mode, I'm not showing the modes. I'm just showing the routes.
Yeah, sorry, the route. So that's what I meant. So that's the route. What you plot shown there
That's the route.
is for single user decoding.
Single user.
So when you go to very low distance, why is this not bunching up? There shouldn't be much benefit from using any of the other.
That's what I think he said. Did I misunderstand the question?
So you're saying this red round and should be coinciding with this.
Yeah, as you go further down,
Yeah.
Lower lower distance. Actually, I'm not seeing why.
I mean, I think this particular gain you're getting is due to little more. I think you have to, after 1 gives to 2, they are going to bunch it. After the closer user to 1 gets it, he's going to help the destination with some more. I have to look at the modes. But
So you think your conjecture is that the modes being used for successive decoding are 1, 2, and then 1, 2, and 5. Basically, like 2 goes to 5 and 1 goes to 5.
That's my conjecture.
And on the right,
On the right, here, I think they are just single user decoding, and I think there are much
each
more.
one is helping.
I think, okay, so this is what I think. So basically here, the single user decoding is also there, and also there is modes due to the successive decoding, but they are not really any better.
Why is this a guess? I mean, you got the modes. I really must be missing the modes.
I got the modes, but I don't have it with me, and I don't remember what the modes are.
But we go back and look.
I can go back and look. Yeah.
It seems like on the far right, you're so noise limited
Yes.
that it doesn't really matter. Simultaneous transmissions don't matter.
That's right.
You don't get any benefit with two transmitters sending at the
Yes.
same time. So that part is probably okay.
And then you'll give us your conclusions, and then you'll tell us how you use these modes with the spectrums, or have we already done spectrum server?
That's it. So this is how we use them. I mean, the spectrum server, this gives us the idea, insight about how we can run these systems.
Okay, great.
Okay, so here is a simulation result, single user decoding alone, and what is the optimal effective number of hops? So basically, if we go 4 hops, obviously for a smaller distance it's bad, and it is good at higher distance, and for single hop route comes down. And optimal multipath routing. So basically, you can do like more like pipelining kind of things. This will be the optimal routes. Okay, so the universal cross-layer design framework, as I said, you have multiple utilities, and this is given by the C matrix, and this is given by the road matrix, and now based on the flow constraints, we can do this scheduling. And, okay, so I'm going to skip. This is basically for a single hop network, we have this particular theorem, which says that for non-zero link gains for interference channel kind of thing, maximizing the minimum flow leads to equal flows in all sessions. So basically, if you want to find the maximum rate, just try to solve the maximizing the min rate linear program, and you'll get it.
So that's a new result.
That's a result which we found, and we also found that result is there in the literature. So consider this particular example.
Wait, back up. You confused me. This feels like, I mean, networking's been around a long time.
Yes.
So this feels like a Gallagher versus this networking result, but I can be
No,
wrong.
it's not. This result was known very sometime in 2005 or something, 2005. This particular network, where for a wireless network, what is the maximum rate?
This network isn't isomorphic with other older fixed networks.
No, I'll show you.
Asking.
I'll show you an example. Okay, so let's consider this example, like a wireline network. So basically, maximum pair is like you have two constraints like this, and you want to find the maximum pair rate here. You just maximize the min rate, but that's not this is the max common rate thing, but that is 4,4. But the maximum pair rate here is 6,4. This is for a wireline case kind of thing. But for an interference network like this, maximizing the common rate is this, and that's also the max common rate basically. This is also the max.
There's link interactions, is
Yes.
what you're telling me, and that's what makes the problem. Yeah. Great, thank you.
Yeah, So this was known. I mean, after we found it independently, but we saw that this people called it solidarity property. And he said, I mean, if you decrease the flow in link I, you can strictly increase the flow in J because of the non-zero linkings. And we showed that the Gaussian solidarity holds for Gaussian independent model, like this. And for it doesn't hold for this kind of schemes where there is multiple axes.
So the points you've drawn here are the max power points.
Yeah, max common rate is max min rate.
The green circles are the max power.
Yeah, green circles are those points in the columns in the C matrix.
What I'm saying is that you're picking from just 1, 0, 0, 1, and 1, 1.
Yes. Basically, this is just the convex hull of this will give you the rate region. Okay, so this is all I have. So in summary, in relays we saw modest rate improvements and we talked about peak power and average power savings. And of course, there's a lot of challenges as Ashwin pointed out and we discussed this. And in the centralized scheduling framework, it gives insight into the operating regimes of interference limited wireless networks. Single source destination networks, PHY advances, which have been there in the PHY advances, it needs to be re-examined with multi-source network settings. So that's all I have. And before I complete the talk, I have to thank a lot of people. First of all, my advisors, Roy, Narayan, and Jerry. They've been. I wouldn't have been standing here but for them. And my committee members, both of them agreed very happily to serve on my committee. And Rinaldo and his group at Bell Labs. I learned a lot. I spent 1 year in Crawford Hill, and I learned a lot in his group. And of course, I was very lucky to work with Jack and Ashwin at Qualcomm, and I learned a lot in Ashwin's group also. And WinLab faculty and staff, they've been amazing. The alumni, I've interacted a lot, and with seminar series and all these things. And all my friends who are sitting here, and so you've been great. Thanks.
Here we go.